The office isn't quite what it seems this evening. The lamp still throws its familiar pool of light across the desk, but the shadows don't settle the way they should, as if the room has acquired an extra fold that the eye can't quite follow. A draft moves through the papers without touching them, the faint suggestion of distance bending in a place where distance shouldn't bend at all. In the glass of the window, the city lights look slightly doubled, like there are two routes for every reflection to take. And on my desk, waiting in that calm circle of light, is a case file with a single word on the tab: Wormholes. Hello there, and welcome to Science to Sleep To. If we haven't met yet, I'm Madeline Rowe, an astrophysicist turned private eye, trading telescope time for case files and calm explanations. Tonight's investigation is a quiet one, filed under geometry and impossibility, under shortcuts that may exist in equations even when the universe refuses to build them. So settle in close, let the room grow softer around the edges, and we'll open the folder together, slowly, carefully, one page at a time. And if you'd like these case files to keep finding their way to your desk, you can subscribe. Then we'll let the night take it from there. Now, one more thing before we slip away. If your eyes are open, they can soften. If they are closed, that is fine too. Either way, we will move slowly, sentence by sentence, like turning pages without hurrying. Okay, here we go. The word wormhole sounds like something you could point at, but in general relativity, the object is the metric. It is the rule that tells spacetime how to measure distance and time. A wormhole is a particular arrangement of that rule, an arrangement that creates two exterior regions and a connecting throat between them. In the simplest picture, there are two mouths. Each mouth is an opening into the throat, sitting in some surrounding space-time. Between them is a minimal area surface, the throat itself. If the throat stays open, a traveller could pass from one side to the other, but that "if" carries the weight of decades. The case file begins, as many do, with history. In 1916, shortly after the Schwarzschild solution appeared, a tunnel-like geometry was noted in the mathematics. Later, Einstein and Rosen described a bridge connecting regions of a maximally extended black hole, spacetime. John Wheeler eventually gave the idea its name, and its cultural life began. But the original Einstein-Rosen bridge is not a usable passage. The reason is quiet and absolute. In the standard black hole bridge, horizons and singularities prevent a two-way crossing. The geometry connects regions, yes, but causal structure blocks the route. It is like drawing a doorway onto a wall that still has no opening. A bridge in the diagram, not a corridor you can walk. The version most people mean by traversable wormhole arrived later. Morris and Thorne, thinking carefully about what would be required for passage, wrote down conditions for a human-friendly geometry. Gentle tides, tolerable accelerations, and a throat wide enough to fit through. When they did, the requirement appeared almost immediately. You need matter that behaves in an unfamiliar way. This is the moment many stories skip. They leap from tunnel to trip. We will not. We will stay with the requirement, because it is the main reason wormholes remain theoretical. In general relativity, matter and energy are described by the stress-energy tensor. It encodes densities, pressures, and energy flows. The Einstein equations tie that tensor to curvature. So if you want a particular curvature, you are implicitly asking for a particular pattern of energy. A traversable wormhole asks for a pattern that violates familiar energy conditions. The easiest one to mention is the null energy condition. Loosely, it says that for any light-like direction, the energy measured along that direction is non-negative. Many classical forms of matter obey it. The geometry of a wormhole throat, however, wants the opposite sign in just the right place. It wants a flaring out that ordinary matter does not support. A related condition, the averaged null energy condition, is even stricter in spirit. Instead of checking energy at a point, it averages along an entire null geodesic. In many quantum field theories, averaged conditions are expected to hold in broad circumstances. Yet, careful work shows there are subtle loopholes in special settings. Loopholes that keep causality safe while permitting limited negative energy effects. This is where the phrase exotic matter comes from. It does not have to be magical, it has to be unusual in its stress energy. Negative energy density or negative energy flux in certain directions is the simplest shorthand. Quantum theory can produce negative energy in small, constrained ways. The keywords are small and constrained. Quantum inequalities limit how much negative energy you can have, for how long, and over what region. The universe seems to allow brief dips below zero, not vast seas of it. That makes macroscopic, stable wormholes very hard to support. Hard, but not logically forbidden by the equations alone. I turn a page in the file. The next section is a diagram in words. Two asymptotic regions. A throat, a choice of coordinates that makes the throat look calm. And then, a reminder scribbled in the margin. Calm in coordinates is not the same as stable in dynamics. Stability is the second great hurdle. Even if you can write down a traversable solution, you must ask what happens when the universe nudges it. A passing wave of ordinary matter, a little radiation. A small pulse in whatever field is holding the throat open. Some wormhole solutions respond by collapsing. A classic example is the Ellis wormhole, often discussed alongside the Morris-Thorne picture. It is supported by a scalar field with an unusual sign in its gravitational coupling, sometimes described as a ghost scalar. In numerical studies, this wormhole is unstable against perturbations. A small positive energy pulse can drive the throat toward a black hole horizon. A sufficiently negative energy pulse can push it toward an inflationary expansion of the throat. That is an eerie symmetry. Add ordinary energy, and the tunnel becomes a trap. Add enough negative energy, and the tunnel swells into something like a growing region. The same object, nudged in opposite ways, can resemble a black hole or an expanding universe. The file notes this as a kind of dynamic interconvertibility. In sleepier language, the throat is like a balance point, not a rigid steel ring, more like a soap film stretched in a frame. A gentle tap can change its shape, and the mathematics keeps track of every tap. We can linger over what collapse means without drama. In relativity, collapse is not a crunching sound. It is the formation of a horizon, a surface beyond which signals cannot return. If a traversable wormhole forms a horizon, it stops being a passage and becomes, effectively, a black hole geometry. We can also linger over expansion. Expansion here is not necessarily the whole universe inflating. It is the throat region growing, the trapping horizons shifting, the geometry changing its character. The details depend on the model, the field content, and the perturbation. But the message is steady. Stability is delicate. Another page, another strand of the story. not in asymptotically flat space, but in anti-de Sitter space, where holography provides a second language. Here, wormholes appear not only as geometric curiosities, but as tools for thinking about quantum information. The file's tone becomes both more technical and more surprising. In ADS/CFT, an eternal black hole in the bulk can correspond to a particular entangled state of two boundary theories. The thermofield double state is the classic example. In the bulk picture, the two sides of the eternal black hole are connected by an Einstein-Rosen bridge. Again, that bridge is not normally traversable. Signals fall into the interior and meet the singularity rather than crossing to the other boundary. And then comes the trick. Not a loophole in causality, but a controlled deformation. If you couple the two boundary theories in a particular way, you can change the bulk stress energy. That change can create a region of negative null energy that opens the bridge, briefly, into a traversable channel. In modern language, this is associated with the Gao-Jafferis wall construction. This does not give you a free shortcut through our universe. It gives you a carefully engineered path in a specific gravitational setting with specific boundary interactions. The two sides must be coupled, meaning information is being allowed to flow by the rules you impose. From the boundary perspective, the protocol resembles quantum teleportation. From the bulk perspective, it resembles sending a message through a throat. The file underlines a comforting point. Traversable does not automatically mean faster than light. Local physics still respects light cones. The apparent shortcut is global geometry, not local violation. And in the holographic constructions, the boundary coupling ensures the overall story remains causal. There is a phrase that floats around this part of the literature: ER equals EPR. The conjecture that entanglement and wormhole-like connections are two faces of a deeper structure. In this view, some wormholes are not tunnels for spacecraft, but bookkeeping devices for quantum correlations. A geometry that encodes how systems share information. The file is careful with its claims. It does not say every entangled pair hides a macroscopic bridge. It says there are settings where a geometric connection is a useful dual description of entanglement. Useful, precise, and still within the known rules. That carefulness is part of the reason this topic feels like science, not myth. I pause at the edge of the page. The lamp hums faintly. In the quiet, it is easier to notice how many different wormholes exist in physics. Lorentzian wormholes with time flowing through them, Euclidean wormholes appearing in path integrals as saddles and instantons. Some are about travel, some are about averages, some are about entropy curves and the accounting of information. For this case file, we will keep returning to one practical question. What would it take for a wormhole to exist as an astrophysical object? Not as a diagram, but as something in the sky. Something that bends light and tugs stars. Something a telescope could, in principle, notice. The file offers one formation idea from higher dimensional models. In brain world pictures, our familiar universe is like a four-dimensional surface embedded in a larger space. Two such brains can sit near each other in the extra dimension. If massive objects reside on each brain, their gravity can pull the brains toward one another. Brain tension resists that pull, like an elastic sheet resisting deformation. If attraction wins over tension, the brains can deform until the regions near the masses touch. In that touching, a wormhole-like connection can form. In this framework, the role of negative energy is effectively played by the brane tension. The mechanism uses classical gravity in the higher dimensional bulk, rather than trying to stockpile macroscopic negative energy in our usual 4 dimensions. The file notes, gently, that this produces wormhole-like structures whose precise local metric depends on the specific objects involved. It also notes a sober detail. If the objects are black holes, horizons will make the resulting connection non-traversable. If the objects are horizonless, like neutron stars in some scenarios, traversability becomes less obviously blocked. More massive and more compact objects tend to satisfy the formation conditions more easily. And then, once again, stability becomes the open question. Stability appears everywhere in this file. Even when formation is plausible, longevity is not guaranteed. A long throat may prefer to fragment into shorter pieces, the way some systems lower energy by changing shape. To know, one needs detailed analysis and, often, numerical simulations. The universe does not sign contracts with our diagrams. Another page turns. Now the case file becomes observational. If wormholes exist, how could we tell? We do not need them to be doorways for travel. We only need them to have gravity. Gravity leaves fingerprints. The most straightforward fingerprint is lensing. Any compact mass bends light, producing magnification, multiple images, or rings depending on alignment. A wormhole can also lens, but the details can differ from a black hole with the same mass. In some models, the throat geometry affects deflection angles, time delays, and image structure. With enough precision, those differences could be compared to data. Another method is micro-lensing. When a compact object passes in front of a background star, the star's light brightens in a characteristic curve. Wormholes could, in principle, produce micro-lensing events with subtle departures from standard shapes. The problem is not the mathematics, the problem is rarity and ambiguity. The file also mentions orbital perturbations. Near the supermassive black hole at our galaxy's centre, stars follow tight, fast orbits. Their motion is measured precisely enough to test relativity in the strong field regime. If a wormhole-like influence were present, it could produce small deviations from expected orbits. Subtle, but perhaps detectable with long-term monitoring. There is an even more precise clock in the cosmos: pulsars, rotating neutron stars that send beams with remarkable regularity. If a pulsar orbited a compact object, tiny changes in gravity could shift arrival times in measurable ways. Some proposals suggest that a perturbing mass on the far side of a wormhole could imprint itself on pulsar timing. Another fingerprint comes not in light, but in space-time vibrations. Gravitational waves carry ring-down signals after mergers, like a struck bell. In some wormhole models, reflections from the throat can create delayed echoes in the ring-down. An echo pattern, if convincingly detected, would be an unusual clue. But nature can be noisy, and confidence requires care. The file keeps repeating a phrase that feels honest. No direct detection so far. It notes that current observations, including images of black hole shadows, tend to favour standard Kerr black holes in the cases we have measured well. Yet it also notes that future instruments will sharpen these tests. And the search continues, not because wormholes are expected, but because gravity is worth interrogating wherever we can. I set that page aside. In the margin of the folder, I've drawn a simple loop. Geometry to matter, matter to stability, stability to observation, observation back to geometry. This is the rhythm of the whole case. Let's return, slowly, to what a wormhole is, in the most minimal sense. It is a space-time with a non-trivial topology. a path that cannot be continuously shrunk to a point without leaving the space. In ordinary flat space, loops can shrink away. In a wormhole geometry, some loops wrap the throat and cannot be erased. That topological feature is a deep reason wormholes feel otherworldly. They suggest that spacetime is not only curved, but connected in surprising ways. Yet, topology alone does not guarantee traversability. A mountain pass is a connection, but it still might be blocked by ice. Wormholes are like that, but with horizons and energy conditions playing the role of ice. There is also the question of scale. Quantum gravity pictures sometimes include microscopic wormholes flickering in what people call quantum foam. These would be tiny, transient, and not traversable in any practical way. They might influence physics indirectly, as contributions to path integrals or effective couplings. The file treats these as plausible within certain frameworks, but not as portals. The macroscopic wormhole, the one with a throat you could, in principle, send a probe through, is a different class of problem. Here, engineering is not metal and bolts, it is stress energy. You would need to arrange matter fields so that the throat remains open, while tidal forces remain gentle. And you would need to protect that arrangement from disruption by ordinary radiation and nearby matter. The file's language here becomes almost soothing in its strictness. A necessary condition, a sufficient condition, a bound, a caveat. It is as if the mathematics is teaching patience, and then, as if to reward patience, the file returns to holography again. In those constructions, the exotic ingredient is not a bucket of negative energy. It is a controlled interaction between two quantum systems. The negative energy appears as a consequence of quantum effects and boundary conditions, carefully arranged. Traversability becomes a protocol rather than a permanent structure. That difference matters. It suggests that wormhole can sometimes mean a quantum channel with a geometric jewel. Not a tunnel for ships, but a tool for understanding how information moves in gravitational settings. In that sense, wormholes have already been useful to physics, even without existing as objects you can point to in the sky. They are working ideas. I lean back slightly in my chair. The quiet of the room holds, and we can take a slower walk through a single concept that keeps reappearing. The idea of a null geodesic, a path that light would take. In relativity, light defines the skeleton of causality. Energy conditions are often phrased in terms of these null paths. They say, in effect, that light rays focus under gravity in predictable ways if matter is ordinary. The Ray-Choudhury equation describes this focusing. In many situations, focusing leads to the formation of trapped surfaces and eventually singularity theorems. A traversable wormhole wants the opposite of focusing at the throat. It wants defocusing, a gentle spreading of neighbouring light rays. That defocusing is what pushes against collapse and keeps the throat open. And defocusing in classical gravity usually demands a violation of the null energy condition. So the geometry and the energy condition are two views of the same constraint. This is a helpful way to keep the story straight. We are not searching for a particular kind of matter because it sounds exotic. We are searching for it because the equations insist on it. If the throat flares out, the stress energy must allow it. If the stress energy does not allow it, the throat pinches. In the Ellis wormhole story, the supporting field is already exotic. Yet even then, perturbations can ruin the balance. That is a second lesson. Exotic does not mean stable. It only means the sign is right at the throat, at least in the static solution. In some modified gravity theories, people add higher curvature terms. Gauss-Bonnet gravity is one example, motivated by string-inspired corrections. One might hope such corrections could stabilize wormhole geometries, but numerical studies of Ellis-type wormholes with Gauss-Bonnet terms show that instability still appears. The throat tends to evolve toward expansion or black hole formation, depending on parameters and perturbations. Again, no drama, just the universe preferring one configuration over another. If a static wormhole is like a pencil balanced on its tip, most real environments will knock it over. Not with malice, with inevitability. I flip to a page marked Misconceptions. The first line says, a wormhole is not necessarily a time machine. The second line says, but some wormholes can be arranged to create closed time-like curves. And then it adds, carefully, this is speculative and likely constrained. That is the right tone for this topic. The time machine idea usually comes from moving one mouth relative to the other, creating time dilation differences. If a traversable wormhole existed and you could accelerate one mouth and bring it back, the mouths could become time-shifted. In principle, that can create paths that return to earlier times in some coordinate sense. But in principle is where the story stays, because it requires a stable, traversable wormhole to begin with. And quantum effects may enforce chronology protection, though the full story is not settled. For sleep, it is enough to hold one thought. Wormholes do not automatically break physics. They test physics. They sit at the boundary where geometry, quantum fields, and causality negotiate. And even when they do not exist in nature, the act of trying to understand them sharpens what we know. Another page is a slow catalogue. Traversable wormholes with thin shells. Wormholes supported by scalar fields. Wormholes in modified gravity. Wormholes in ADS used as quantum channels. Multi-boundary wormholes encoding multipartite entanglement. The file does not demand we memorize them, it only asks that we notice the pattern. Each construction is a bargain. You get a throat, but you pay with assumptions. You get traversability, but you pay with negative energy, boundary couplings, extra dimensions, or carefully tuned fields. The more humanly traversable the wormhole becomes, the more elaborate the bargain tends to be. And the more constrained, the less it resembles a wild portal in open space. This is a quiet truth that makes the topic calmer. Wormholes are not an escape from physics. They are an intense demand for physics. Now let's drift gently into a different kind of explanation. Not less scientific, just slower. We will take one wormhole purely as a geometric model and walk around it with words, like tracing a coastline with a finger on a map. Start far away from the throat, in an exterior region where space-time looks ordinary. Distances behave as expected. Clocks tick normally for distant observers. As you move inward, the geometry gently deviates. The area of spheres stops shrinking at a point and reaches a minimum. That minimum area surface is the throat. At the throat, the geometry turns around in a way that does not require a singularity. Past the throat, the area expands again, but now you are in another region, another exterior, potentially far away in space, or even in a different asymptotic universe in the mathematical sense. Two outsides, one middle. If the wormhole is traversable, you can cross the minimum and keep going. If it is not traversable, something stops you. A horizon, a pinch-off, a burst of instability that changes the geometry while you are still on your way. In many realistic scenarios, the stopping happens faster than the crossing. That crossing time is another gentle detail. Even in theoretical models, there can be a transit time through the throat that must be shorter than the time it takes for the wormhole to destabilize. In some constructions, mouths gravitationally attract and would merge on a timescale that depends on their separation. So to be useful, even as a mathematical channel, a wormhole must last long enough relative to its own geometry. Again, the theme is patience. I return to the desk, to the folder, to the steady black ink. The file is thick, but it is not chaotic. It is built from repeated constraints: energy conditions, stability, causality, observability. Let's take them one at a time, again, but in a softer voice. Energy conditions ask whether matter can support the geometry. Stability asks whether the geometry persists under perturbations. Causality asks whether signals behave sensibly and whether paradoxes appear. Observability asks whether any of this could ever be tested. Those 4 questions are enough to fill an entire night of quiet thinking. The file opens a side pocket. Inside is a small note about speculative frameworks. One note describes wormholes as transient events requiring symmetric conditions at both ends. It is a conceptual proposal rather than a fully developed mathematical model. We can hold it lightly as a reminder that people still search for formation stories that do not rely on impossible amounts of negative energy. And then we return to firmer ground. Because the firm ground here is already strange enough. General relativity allows wormhole geometries. Quantum field theory allows small negative energies. Holography suggests deep links between entanglement and geometry. Each of those statements is sober and supported, even if the combined dream of interstellar tunnels remains out of reach. Now, we can settle into a longer, slower tour. The kind of tour that gently repeats, so your mind can let go. I will read through the case file as if I am filing it away, page by page. If you catch a detail, it is yours to keep. If you miss one, the story still holds. Page 1. Definition. A wormhole is a spacetime connection between 2 regions, with a throat that can, in some models, be traversed. In most classical settings, traversability requires violation of the null energy condition. The geometry is real as a solution, but its matter requirements may be physically unrealistic at macroscopic scales. Page 2. History. Flamm's early observation of tunnel-like geometry in Schwarzschild spacetime. Einstein and Rosen's bridge, which is non-traversable. Wheeler's naming and the later development of traversable criteria by Morris and Thorne. The cultural story follows the mathematics, but the mathematics sets strict limits. Page 3. Energy. The null energy condition and the averaged null energy condition act like guardrails. Traversable wormholes require a controlled way around those guardrails. Quantum theory permits local negative energies, but limits them with inequalities. Macroscopic, long-lived negative energy is not known to be achievable. Page 4. Dynamics. The Ellis wormhole, supported by a ghost scalar field, is a simple, traversable model. Numerical studies show it is unstable to perturbations. Positive energy pulses tend to collapse the throat into a black hole horizon. Negative energy pulses can drive the throat toward expansion. Page 5. Modified gravity. Higher curvature corrections, like Gauss-Bonnet terms, change the equations, but do not automatically stabilize the simplest wormholes. Instability remains a common feature. The precise outcome depends on parameters, but the pencil on its tip feeling persists. a static throat is rarely a guaranteed throat. Page 6. Holography. In ADS/CFT, wormhole geometries appear as jewels of entangled states and quantum information processes. An eternal ADS black hole corresponds to a thermofield double state and an Einstein-Rosen bridge. Coupling the two boundary systems can create a traversable channel by generating negative null energy in the bulk. Traversability here resembles a teleportation protocol consistent with causality. Page 7. Formation. In some brain world models, two massive objects on nearby brains can gravitationally deform the brains until they touch, forming a wormhole-like connection. Brain tension plays a role analogous to negative energy support. More massive and more compact objects are more likely to satisfy formation conditions. Traversability depends on horizons and on stability, which remains uncertain. Page 8. Detection. Proposed observational signatures include unusual lensing patterns, microlensing curves, orbital perturbations near supermassive compact objects, and possible gravitational wave echoes. Pulsar timing in strong gravitational fields could reveal anomalies if a wormhole-like influence existed. Some ideas involve polarization effects or spectral line differences in accretion environments. No confirmed detection exists, and many signatures are hard to disentangle from more ordinary astrophysics, and that is the core of the file. But the file is not finished, because physics is not finished. So we can let the remaining pages be softer repetitions and gentle expansions, the kind that your mind can drift through without holding tight. We will circle the same truths from different angles, the way a planet looks different at dawn and dusk. Consider, again, the difference between a shortcut and a violation. A shortcut is global. A violation is local. Wormholes, when they appear, are global features of the spacetime manifold. Locally, near any small region, physics can still look like ordinary relativity. That is why wormholes can be discussed without instantly breaking everything. They are not permission slips to ignore light cones. They are proposals for how light cones might be arranged across a larger space. And when energy conditions constrain how light cones can be arranged, wormholes become rare. Not forbidden by imagination, constrained by equations. Another gentle expansion is the idea of two mouths. In some contexts, mouths are literal asymptotic regions. In holography, mouths can map to boundaries of quantum theories. In brain scenarios, mouths might correspond to nearby regions on different brains. The language stays the same, but the underlying meaning shifts with the framework. That shift is part of what makes wormholes feel like a whole landscape rather than a single object. The landscape has valleys of well-understood math and peaks of speculation. We are walking mostly in the valleys tonight, the valleys where energy conditions, stability analysis, and dualities can be written down cleanly, where the file has footnotes and the margins have equations. If your thoughts wander to films and stories, you can let them drift away like mist. We will stay with a quieter picture, a wormhole as a question posed to the universe. Can spacetime connect distant regions without tearing? Can it do so while remaining stable? Can it do so with matter that is physically reasonable? The current answer is cautious. We do not know of any naturally occurring macroscopic traversable wormholes. We do know of many mathematical wormhole solutions. We do know that quantum effects can violate energy conditions in limited ways. We do know that certain holographic settings realize traversable channels under controlled couplings. And we do know that observational tests of compact objects keep improving. In other words, the file ends with a frontier, not a verdict. and that is a peaceful place to rest. A frontier does not demand closure, it only asks for careful steps, so we can take those steps slowly and then stop and let the night do what it does. I close the folder halfway, not sealing it, just easing it shut. The lamplight narrows across the paper. The office remains quiet, patient, and ordinary. Outside, the universe continues to curve and expand, whether or not it contains tunnels. And inside, we can let the thought of wormholes become simple again. Geometry, energy, stability, observation. 4 soft words. 4 pages in a cosmic case file. Geometry. The throat as a minimum area surface. The mouths as exterior regions. The path through the middle that exists in the metric. A connection that is real in equations, even if it is not realized in nature. Energy. The stress-energy tensor as the source of curvature. The null energy condition as a guiding constraint. Negative energy as a rare and tightly limited quantum resource. The need for defocusing at the throat and the price that defocusing implies. Stability. Perturbations as inevitable. The Ellis wormhole's tendency to collapse or expand when nudged. The difficulty of building a throat that remains open under the universe's ordinary noise. The reminder that static solutions are not promises, only snapshots. Observation, lensing and microlensing, stellar orbits and pulsar timing, gravitational wave ringdowns, and the possibility of echoes. The slow improvement of instruments and the patient comparison of models to data. With that, we can let the case file rest on the desk. You do not need to hold it anymore. The universe can keep its secrets for now, and you can let your thoughts drift gently away from tunnels and thresholds. Back to the quiet room. A soft lamp, a calm desk, a closed folder, and a steady breath doing what it has always done. In, out, in, out. If you are still listening, we can take one last slow loop through the central idea. A wormhole is a geometry that connects. To keep it open, you need defocusing of light rays at the throat. Defocusing implies unusual stress energy, often involving negative energy along null directions. Quantum physics can provide small, constrained negative energy, and special holographic setups can engineer traversable channels. But no ordinary astrophysical setting is known to provide the required conditions at macroscopic scale. Before we close the folder completely, there is one more gentle thread worth filing in place. It is the difference between a picture of space and the full story of spacetime. Many wormhole drawings show a curved sheet with a dip, as if space were a fabric you could hold in your hands. Those drawings can be helpful, but they can also hide what matters most. In relativity, time is woven into the geometry, and causal structure decides what can cross and what cannot. In a quiet teaching example, one takes a single moment in time and looks at a spatial slice. For a Schwarzschild black hole, that slice can be drawn as an embedding surface that flares outward like a smooth funnel. On that slice, it can look as if 2 exterior regions meet at a narrow neck. That neck is sometimes called a bridge, and it is real in the geometry of the slice. But a slice is not a journey. A slice is a snapshot. If you follow the full spacetime, the bridge is fleeting. It opens and closes in such a way that no signal can use it to pass from one exterior to the other. In the maximally extended description, the 2 regions are connected, yet the connection is sealed by horizons and singularities. What looks like a corridor in a diagram becomes a one-way fall in the causal story. This is one of the most useful lessons in the entire file. When physics says non-traversable, it is not dismissing the bridge. It is being precise about light cones. Light cones are the local rulebook for what can influence what. In a non-traversable bridge, the cones tip and pinch so that any forward-moving path gets trapped. The geometry connects, but the cones forbid the crossing. This is why the word shortcut needs care. A shortcut is only a shortcut if a causal path exists through it. If the only paths go into a horizon, the connection is mathematical but not usable for signalling. And if the only way to make a causal path is to introduce negative energy, then the shortcut comes with a strict price. The file keeps that price tag visible, even when the room is quiet. Another page in the back pocket mentions a construction that sounds almost like careful carpentry. Cut 2 regions out of spacetime, trim them, then join the boundaries. This is the spirit of thin shell wormholes, sometimes called cut and paste wormholes. The throat is a shell where the gluing happens. The gluing is not free. At the shell, the curvature jumps, and that jump corresponds to stress energy concentrated on the surface. In many simple cases, the surface energy density comes out negative. So even in this tidy construction, the same requirement returns. You can build the geometry, but you pay with exotic stress energy at the seam. There is something calming about seeing the requirement reappear in different languages. It means the difficulty is not a quirk of one model. It is structural. It is woven into how gravity focuses light and how throats must flare outward. Different constructions, same constraint, written in different handwriting. The file then offers a quiet reminder about quantum fields. Quantum theory does allow negative energy densities in limited ways. The Casimir effect is a famous example of how boundary conditions can lower the vacuum energy between plates. There are also squeezed states of light that produce brief negative energy fluxes. These effects are real, measured, and still tightly bounded. The bounds matter because they stop the story from becoming limitless. Quantum inequalities act like timers and measuring cups. If the energy goes negative, it cannot stay that way arbitrarily long in an arbitrarily large region, at least in standard settings. The deeper the dip, the shorter the allowed duration. This is part of why macroscopic wormholes remain so hard to sustain. Even so, it is worth holding a gentle nuance. Hard to sustain is not the same as forbidden by logic. Physics often lives in that space between. The equations allow, the inequalities restrict, and nature chooses what is easy. Wormholes sit in the territory of what is allowed, but not obviously easy. The file's holography section returns here with a soft click of coherence. In the Traversable ADS constructions, the negative energy is not poured in by hand. It emerges from a specific interaction that couples the two boundaries for a controlled interval. One can think of it as briefly opening a quantum valve between two systems. In the bulk language, that valve shows up as a sliver of negative null energy that nudges the bridge open. The briefly is important. Traversability is often a window, not a permanent feature. A message can pass if it is timed correctly, like a boat crossing a lock when the gate is open. The lock closes again, and the geometry returns to non-traversable. This kind of wormhole is more like a protocol than a tunnel, and that brings a calm reinterpretation of the word gate. In many stories, a gate is a glowing circle in space. In the hard science versions, a gate is a condition, a period in which the stress energy meets the requirement, a moment when the causal structure allows the crossing. With that in mind, we can drift back to astrophysics again. Suppose a compact object were not a black hole, but something that mimics one at a distance. A wormhole throat can, in some models, act like such a mimic. It can produce a gravitational field similar to a black hole's, while lacking a true event horizon. If so, the differences would hide in the details of light paths and time delays. Light near a compact object can orbit in unstable photon rings. That is part of why black hole images show a bright ring-like structure. In wormhole models, the throat can alter the locations and stability of these photon paths. It can also allow light to pass through and re-emerge, creating additional image contributions from the far side. In principle, this could change the brightness pattern or the spectrum of what we see. Microlensing is another place to look for subtle oddness. A conventional lens produces a characteristic brightening curve as alignment changes. A wormhole lens might produce additional features, such as extra peaks or an unusual symmetry, depending on its throat and the path families available. But the universe offers many ways to make odd curves, including binaries, extended sources, and stellar variability. So the case file treats microlensing as suggestive, not decisive. Gravitational waves, too, are treated with caution. The idea of echoes is appealing because it sounds like a clean signature, a pulse, then a delayed reflection, then another. But echoes depend on boundary-like structures and reflectivity, and astrophysical noise can mimic repeating patterns. The file's tone stays steady. Interesting. Not settled. There's also a quieter signature that is sometimes overlooked: time delay. In strong gravitational lensing, different light paths arrive at different times. A wormhole that provides an additional family of paths could create a distinctive delay structure. If a variable source flares, the pattern of repeated flares in the images could carry information about the lens geometry. This is where patience becomes an observational tool. You watch. You wait. You compare models to long sequences of data. Astronomy is often a science of slow accumulation, and wormholes, if they exist at all, would likely reveal themselves only through slow accumulation. The file sets down another calm boundary between what is known and what is hoped. Known. Black holes exist, and General Relativity describes many of their features with remarkable accuracy. Known. Quantum fields can violate energy conditions locally in restricted ways. Hoped. That such violations could be arranged to support macroscopic throats without instability. The file does not scold the hope. It simply files it under open. And then, for sleep, it offers a gentle repetition, like a lullaby made of constraints. Wormholes are allowed as solutions. Traversable wormholes are constrained by energy conditions and stability. Holographic wormholes can be traversable as protocols under controlled couplings. Astrophysical wormholes, if they exist, would need signatures that survive the universe's ordinary messiness. I place a small bookmark in the file at the page labelled Enough. Not because the topic ends, but because the mind can stop holding it. The lamplight is warm, and the room is steady. Geometry can return to being a quiet word, and the idea of a throat in spacetime can soften into something abstract and harmless, like a curve in a distant equation. One last, very simple thought stays on the desk like a smooth stone. If a traversable throat existed, even briefly, the first thing you would try is not a person. It would be a signal, a pulse of light, or a radio ping sent with a timestamp. The question would be humble. Does anything come out the other side? In the quiet logic of relativity, even that experiment has layers. You would ask whether the pulse arrives earlier than any conventional route through ordinary space. You would ask whether the pulse is redshifted or distorted by the throat's curvature. You would ask whether the act of sending it back reacts on the geometry enough to close the window. And you would ask whether quantum noise and stability limits erase the channel before it can be used twice. For now, those questions remain filed under beautiful, unanswered. And that is a gentle category. It means the universe is still teaching us. It means there are still edges where mathematics and measurement have not yet met. You can let that edge fade into the background, like a coastline in mist. The folder can stay slightly open on the desk, not because we are worried it will vanish, but because curiosity does not need a lock. If you notice your thoughts looping, that is normal. This topic is made of loops and bridges and repeated constraints, so we will answer the loop with a softer loop, and then let it go. Just a calm ending to the thought. Nothing to solve. The file ends there, not with a slam, but with a quiet click. The lamp stays on a little longer, and the rest of the room stays still. You can let the last words fade, and let sleep do the rest.